So we've got, and let me open the notes. Where are they? I said these three notes. I'll just open them when they're required. As anyway, so you first question. That's not organic. Organic. We've got no. That's not organic. Just a second. This is not organic. I think we've already done this paper, I guess. Just let me double check this. Yeah, I guess we actually did this one last time. Let me open another one. Okay, let's do summer 20 question paper 4-1. Just 1 second. So summer 20 and 4-1.
Sure.
G.
Sir, which topics have you covered in these classes so far for past papers?
Hey, we're going to cover all of them, TK. We still have some time, so we'll probably go through all of them, TK.
Okay.
So this one we've got organic. This one. The first thing is the molecular formula. This one is about comparison of the acids and bases. So describe and explain the relative. Now the question is about it's about the comparison of basicities. Now all these compounds that have N in them, like NH3, why are they basic? They're basic because the N has a lone pair. It's got negative charge on it, and the H+1 gets very strongly attracted to it. It gets attracted to those lone pairs, which is why this N can accept H+1 ions. So any compound that's got N in it is going to be able to accept H+1 ions. So the idea is this one. I mean, the whole explanation is given in this part 2 of the. I think it's in part 2. So the idea about basicity is it's just the reverse of the comparison of acids. No, I think it's in part 3. Just 1 second. So that's where we study nitrogen bases. Let me just check. So we studied acids. No, it's in part 2. So bases, right? The idea is that the lone pair is going to be attracted to the H+1, right? So you've got a total of 4 bases that you have to study. One of them is your normal ammonia. That's a base. Then you've got alkyl amines. Alkyl amines is that the N has a carbon chain attached to it. So the idea is pretty basic. It's that when you have a carbon chain attached to it, the carbon chain has an electron donating effect. If it has an electron donating effect, you get more electrons on this lone pair. If you've got more electrons, there's going to be a stronger attraction for H+1. Is that clear that this one is going to be a stronger base? Is this clear? Asira, Amina, is this clear?
Yes, sir.
So you got an alkyl chain, there's more negative charge density over here. Similarly, the N can be attached to a benzene. When it's attached to the benzene, the lone pair actually mixes with the benzene electron cloud over here. So the lone pair it's got a lower negative charge density, and so the lone pair on N overlaps with the benzene pi electron cloud. The charge density on the lone pair decreases, and there's less attraction for H+1. So that's a weak base. And this one is not basic at all because, again, you've got a C-double bond. That's an amide. When an N has a C-double bond O next to it, that's an amide. So when you have an amide, it's not basic at all. The reason is that the oxygen has such a strong attraction for electrons. It's so electronegative that the lone pair completely mixes with the oxygen. The lone pair on N overlaps with the pi electron cloud in C-double bond O, as O is highly electronegative. Charge density on the lone pair decreases, and therefore there's very less attraction for H+1. So in both these cases, the lone pair kind of mixes with the electron cloud. Over here, it does that, but to a lesser extent. Over here, the oxygen pulls the electron very, very strongly. And over here, the lone pair is stronger than before because the carbon chain is pushing its electrons onto the lone pair. So that's why the negative charge density over here is a lot stronger. So there's a lot stronger attraction for H+1. So that's the whole idea. These four things. That's about it. Is that clear? Amide, phenylamine, ammonia, alkylamine. Is that clear?
Yes, sir.
So coming back to the question, see, is this clear?
Yes, sir.
Now coming back to the question. The question was, where's the question? You got these five. So I just need to identify. The first one is an amide. It's if you look at S, remember C6H5 is benzene. So that's a benzene, C6H5. And you got a C double bond O and NH2, right? So that's your amide. That's not basic, or that's the least basic. That's the least basic, and you're going to explain the whole thing. That the lone pair mixes with the C double bond O, overlaps with the pi electron cloud over here. Why? Because the oxygen over here is like really electronegative, so it pulls the electrons. This one over here is your normal phenylamine. It's again C6H5. That's your benzene, and there's an NH2 that's attached right next to it. So this time the lone pair actually mixes with the benzene electron cloud. So this is the least basic. This is also less basic. The lone pair mixes with the electron cloud, and what happens is that the electron density is lesser. And the third one, that's your alkylamine. That's C6H5. That's benzene. So that's your benzene. But then you've got a carbon chain. There's a CH2, and then there's an NH2. So since there is a carbon chain, the carbon chain has an electron donating effect. So the negative charge over here is going to be, it's actually going to be larger. So just remember this fact that all of them have benzenes, but this one is an amide because right next to it, because it doesn't really matter where the benzene is, what's right next to N. If you've got a C double bond O, that's an amide. If right next to N you've got a benzene, that's your phenylamine. And if right next door there's a carbon chain, then you're going to treat it as a carbon chain. That's your normal alkyl amine. So is this clear, this question?
Yes, sir.
And let me quickly. I just wanted to check it's question number 4. Just wanted to check the wording that they're using. Question number 4. So alkyl group is electron donating, so lone pair more able to accept electrons. It's got a higher charge density. There's more attraction for H+1. Lone pair on N overlaps with delocalized system or delocalized electron cloud on benzene, so it's less able to accept. And then there's a presence of electron withdrawing oxygen. Carbonyl group, C double bond O means lone pair is not available to accept. It's not basic at all. So the third one, TK, just like this. The third one, the highly electronegative, as O is highly electronegative, it overlaps with the carbonyl group, which is C double bond O, and decreases, and there's less attraction for H+1. The only thing I think over here in the marking scheme is that in the last one, they're saying that it's not available to accept a proton. So I think you should use the word not available to accept a proton. I mean, I wrote less attraction for H+1. You're gonna write not able to attract H+1. That's better because I did write it's not basic. So anyways, that's the answer to this question. Now the next one is you've got this thing happening, suggest reagents and conditions for reaction 1 and 2, right? So this one is a halogen getting substituted by NH2. That's and it's getting substituted on the carbon chain, not on the benzene. It's got nothing to do with the benzene. This reaction over here has nothing to do with benzene. So what reaction is this? This is what you studied in AS. Let me open AS. That's halogenoalkanes. So in AS, so now in AS you studied that you've got halogenoalkanes, and there were three substitution reactions. You can substitute the halogen with ammonia or with OH or with CN. There were three nucleophilic substitution reactions. So he's talking about one of them. That's he's substituting Br with NH2. For that, you would require ammonia, and that's going to be ethanolic, and that's going to be, and you're going to reflux it. There are actually two conditions. Okay? So remember, this is AS. You can also use ammonia gas plus heat in a sealed tube under pressure. That would also work. So that's one. And then you've got an amide. 1 second. That's the next one. Then you've got an amide. This is an amide. It's N with a acetyl bond O, and it's turning into an amine. So what reaction is this? This is if you open part 3 in oxidation and reduction, we did the reduction of amides. That an amide, if you add LiLH4, that will get reduced to the acetyl bond O will vanish. It will be substituted. The oxygen will be removed and hydrogens will get added to it. So the amide will turn into an amide. So the acetyl bond over here, if you do reduction, that will be gone. So that is this one. So the carbon now has hydrogen attached to it. Previously it had oxygens attached to it. So it's going to be LiAlH4 for this reaction. And that is reduction. Is that clear?
Yes, sir.
Yes. So could you send me the other spider chart that you just opened?
Yes, Vala?
Yes, the one where we just saw the nucleophilic substitution.
This one, right?
Yes.
I'll share that. As anyway, so that's remember that is AS. I've got an A2 one as well, so I'll share that as well. So you've got, going back to the question, we've got state the type of reaction 1, and name the mechanism in reaction 2. So this one was your nucleophilic substitution, and that's a primary halogenoalkane. So primary halogenoalkanes, they undergo SN2 mechanisms. Okay, so I don't think he was being that specific. You just write nucleophilic substitution, and that's reduction. We already wrote reduction for that. Now moving on. Benzene reacts with bromine in the presence of an aluminum bromide catalyst to form bromobenzene. This is a substitution reaction. No addition takes place. Explain why no addition reaction takes place. So why is there no addition reaction taking place in this case? So what happens is that in this case, what happens is that you got a benzene, and I think this is bromination. It's reacting with bromine. Bromine molecules are reacting. Let me open the notes instead of drawing this. You waited I said the part 1. So this part over here, this is what benzene looks like. This is nitration. We're talking about bromination over here. So this is what benzene actually looks like. An sp2 hybridized carbon atom with p orbitals. All of them have an extra p orbital and they start overlapping, right? So what happens is that the bromine molecule over here, it gets polarized. The positive bromine attracts one of the p orbitals and bonds with it. So the pi electron cloud becomes incomplete. And so why is there no addition happening? Why is there a substitution happening? Because the pi electron cloud becomes very unstable. Because somebody took electron away from it, and that was your bromine. The bromine took electron away from it, and it needs to complete its electron deficient now. It's got a positive charge now because one of the electrons is gone. So the H has to leave its electrons over here. So the reason no addition takes place is that the carbocation, this cation that is formed, that is extremely unstable. Is that clear?
Yes, sir.
Yes.
So it's just a 1 mark question, and that's what you're going to write over here. So explain why no addition takes place. Tell them that this particular ion, it's just 1 mark. So it's going to become positive. So the intermediate is highly unstable. So I'm not really sure how they're using or describing it in words. I just so they're talking about. I mean, the wording that they're using. The substitution product is stabilized by delocalization of 6 pi-electron clouds. My statement was kind of exactly the same, but I'm saying saying it in the reverse direction, which is that I mean they're saying that if you have 6 electrons, the delocalized system is stabilized, right? I'm saying the same thing, but in the opposite way, which is I'm saying that this ion over here, when you have 5 electrons, that's unstable. So I guess that will be acceptable as well. That's exactly the opposite of what they're saying, but both things mean the same thing. Okay, is this part clear?
Yes, sir.
Yes.
So now draw the mechanism of the reaction between benzene and Br+1 ions, include all relevant arrows and charges. So all you have to do in this case is draw this mechanism. It's this one. You got benzene. The bromine gets polarized. So now the only difference is that they're saying that use Br+1 instead. So I guess we're not going to draw this part. The Br is already +1. So we're going to use the same exact mechanism, except for the fact that he's saying use Br+1 ions. So the Br+1 ions are going to come in and they're going to get attracted to the electrons, and the electron cloud will become incomplete. And in the next step, the H is the one that will lose electrons and give the electrons back, and that will complete the benzene delocalized electron cloud system. And the H will leave. And he's saying draw the relevant arrows and curly arrows and charges. So I guess we've done that. Okay, so this is okay, that's the only thing. He was using Br+1. That's about it. Is that clear as well?
Yes, sir.
Yes.
I said write an equation to show how the AlBr3 catalyst is reformed. The way it's reformed is, again going back to the notes, the way it's reformed is that you actually, it's talking about AlBr3. Remember, there were 2 catalysts that could be used. You can use FeBr3 or you can use AlBr3. The Al will first gain the Br negative ion, so it will become AlBr4 minus 1. Like over here, it becomes FeBr4 minus 1. So that's the first part. So the catalyst will initially accept the negative Br ion. It will become AlBr4 and it's going to have a -1 charge. When the H+1 is released, that H+1 goes and attracts the Br and it forms HBr. And the AlBr3 catalyst gets reformed. Same thing happening over here. You had an FeBr4 minus 1. Initially, you had an FeBr3. Then it became FeBr4 minus 1. The H+1 then came along, got its Br back. It ended up forming HBr, and the FeBr3 got reformed. So you had to write this reaction. Is that clear?
Yes, sir.
Yes.
I just suggest why bromination of phenols occurs more readily than bromination of benzene. Now that's about derivative compounds, like electrophilic substitution of derivative compounds. So when you have derivative compounds, there are 2 types of derivative compounds. One is 2,4,6 directing, which are activating groups. 2,4,6 directing groups are when you have a benzene and you've got a group that's attached that's electron donating. So the negative charge density on the benzene is no longer evenly distributed. What happens is that on one side, you got more electrons, especially on positions 2 and 6. And all the other benzene electrons, they get concentrated, they get repelled, and they accumulate on the 4 position. So these are activated benzene. The electron donating effect is going to be a lot stronger. So arenes were one that you attach a carbon chain that will activate the benzene. The other ones were phenols, right? The OH does the same. The lone pairs on oxygen, they overlap with benzene, so the electron density over here becomes greater. And all the other electrons in benzene, they become concentrated more on this side. So why is the reaction faster? Because the lone pair on oxygen, they overlap with benzene pi electron cloud, which increases its charge density and also its polarizing power. And you can write that there's going to be more attraction for the electrophile. The positive bromine will be more strongly attracted to a higher charge density electron cloud. Is that clear?
Sir, so does the benzene ring become more stable or less stable when this happens?
It becomes less stable, actually. I mean, less stable means that it's more willing to react. Is that clear?
Yes, sir.
Something that is stable, it's not willing to react, right? Now it's going to be more attracted to bromine, and you're going to have a faster reaction. Bromine will get
All right.
get attached to 2,4,6 position. So remember this. Remember this. That whenever something, whether it's negative charge or whether it's positive charge, whenever something has a higher charge density, it becomes unstable. Why? Because now it's going to be attracted to other things. Now it's going to be more reactive, right? So it's more unstable. Is that clear?
Yes, sir. Got it, sir. Thank you, sir.
So the answer to this part, 2 marks, part B, that's higher electron density. You just have to quote that the lone pair of oxygen, it mixes with the benzene ring electron cloud and gets delocalized on it, and the electron density is higher. So there's more polarizing power and there's going to be more attraction for the electrophile. Now the next part. There are 4 different carbocations with the same formula, C4H9 plus. One structure is given in the table. Suggests the structural formula of 3 other carbocations. So what you have over here is you've got 4 carbons, and he's saying that this one is a carbocation, right? I'm not drawing the hydrogens just for clarity. So what could be the other structures? I could have another one, and it can have 4 carbon atoms, and this one could be a carbocation. Is that clear? The middle one. Or what I can have is I can have 3 carbon in a chain and 1 carbon as a branch, and this could be a carbocation. Or what I can have is I can have the middle one as the carbocation, right? I mean, making this the carbocation, this the carbocation, or this the carbocation, it's kind of the same thing, right? So these are my 4 carbocations, and I can add in the hydrogens. There's going to be 3 hydrogens, there's going to be 2 hydrogens, 3 hydrogens, and there's just going to be 1 H because remember it's missing 1 bond. That's why it's +1. This will be CH3. There'll be 1 H over here. There'll be 3 H's over here. Carbon is making 1 bond, so it's going to be having 2 more bonds with H. Not 4 bonds because it's +1. This is CH3, CH3, and this one will be CH3. Carbon will be making 3 bonds, not the 4th bond because it's a carbocation. Is that clear?
Yes, sir.
Now, benzene reacts with each of these carbocations in separate Friedel-Crafts alkylation reactions. In each reaction, an organic compound with the formula C10H14 is formed. And that's carbon 13 NMR, by the way. So we can ignore this question for now. Or we can actually, I mean, carbon 30 is kind of simple. It's no, but let's ignore that. Let's focus on organic at the moment. Now, the next one is compare and explain the relative acidities of 2-chloropropanoic acid, 3-chloropropanoic acid, and propanoic acid. So propanoic acid is this thing. Not drawing the hydrogens just for clarity. 3-chloropropanoic acid is propanoic acid with a chlorine that's attached to it on the third one. And then you've got 2-chloropropanoic acid. That's propanoic acid. And I've got 2-chloro. That means Cl attached on the second one, right? So which one is the stronger acid? What was the reason for that? Every one of them will lose an H+1, right? So let's make them lose an H+1. I mean, the carboxylic acid group, it loses H+1 ions and they become negatively charged. So the H+1 is lost. And we're going to look at the attraction between. So who's got the greatest negative charge? Like if you look at the first one, it's got a carbon chain. What does a carbon chain do? It pushes electrons onto whatever it's attached to. So what will happen to the negative charge over here? It's going to be larger, right? Is that clear?
Yes, sir.
Yes, sir.
So what will happen to the strength of the ONH bond? Will it be stronger or will it be weaker?
Stronger?
So there's going to be less ionization, right?
Yes, sir.
So this is going to be your least acidic. This is the weakest acid. It's not going to let go of the H+1 because the negative charge would be larger. So there's going to be more attraction between the ONH. So it would be very hard for it to lose H+1 ions. What about these two? Both of them have an electron withdrawing effect, but remember, if the Cl is closer to the carboxylic acid group, the Cl is electron withdrawing, right? So the negative charge over here will be smaller. So if it's smaller, why is it smaller? Because the Cl is pulling electrons away from it, right? So the negative charge will be smaller. If it's smaller, then the attraction will be weaker. It's going to be a weaker OH bond, and therefore there's going to be more ionization. I mean, these two things are not going to be attracting each other that strongly. Is that clear? Asina, clear? Is that clear? I mean, is this clear?
Yes.
Yes, sir.
You'll also have electron withdrawing effect over here as well. But since the Cl is like really far away, the electron withdrawing effect is not going to be that strong. So it's going to be, the negative charge will be smaller, but not that small compared to the first, I mean, the right hand case. Is that clear? I mean, the comparison between these two things, is that clear?
Yes.
Yes, sir.
So we did this. I think it's in part 2. He gets right where we studied bases. Over there, we also talked about the position of the Cl. That was important as well. If you had 2 Cls, there's going to be more electron withdrawing effect. This will be smaller. It's going to ionize more. It's going to be a stronger acid because it will not attract H+1. If you have 1 Cl, then the electron withdrawing effect will be lesser. But if the Cl is like really close, it's going to be really close to the oxygen, then that means there's going to be a stronger electron withdrawing effect. And this will have the least electron withdrawing effect because the Cl is really far away. So, and we did talk about the carbon chains as well, that, I mean, this is Cl substituted. Then you had comparison of carboxylic acids. If you had carbon chains, you got a bigger carbon chain, you'll have more electron donating effect. The negative charge will become larger and it will become a weaker acid because the attraction between the two things will become stronger. So less ionization will happen. So remember all these scenarios and different combinations. So remember this. I said now that's a K question. Now 3 tests were carried out on separate samples of organic acids shown in the table. So one of them is this is methanoic acid. And this one over here is oxalic acid, which is ethane. This is ethane dioic acid. And this one is some acid, and I don't know what the name is, but at least it's not ethane. I mean, eth is 2 carbon atoms, right? This one is a carboxylic acid. This side is also carboxylic acid. So that's dioic acid. Now remember this thing, that when you study oxidation and reduction, and where do you study? That's this part, reduction. So if you go all the way back in part 3, this part, the place where you study the oxidation of alcohols. Remember this, primary alcohols, they turn into aldehydes. Aldehydes, they turn into carboxylic acids. And the reverse also happens. They get reduced to aldehydes, they get reduced back to primary alcohols. Now, remember this thing that when you talk about carboxylic acids, there are two carboxylic acids and only two carboxylic acids that get oxidized. Just two of them. One of them is methylic acid, which gets oxidized by tolerance. Phelling, caminophore, or K2Cr2s, all of them, pretty much all of them. Any oxidizing agent will oxidize methanoic acid to carbon dioxide and water. And there's another one, which is ethane dioic acid. So only these two acids, they get oxidized. So if you look at the chart over here in the question, it's got something to do with that because he's talking about methanoic acid and he's talking about ethane dioic acid as well. So when does methanoic acid get oxidized and the ethane dioic acid does not get oxidized? So when does that happen? Remember, ethane dioic acid gets oxidized only by caminophore, right? And that one gets oxidized by caminophore as well. So if I go back and answer this question, this one will be caminophore. So this one over here will be caminophore, acidified, and the conditions will be you're going to heat with reflux. Why? Because the methanoic acid and the ethane dioic acid are both getting oxidized. And remember, these are the only two acids that get oxidized. So whatever this is, it's not going to get oxidized. Any other carboxylic acid does not get oxidized. So the color change will be purple to colorless. Is that clear?
Yes, sir.
Yes, sir.
So then the first one could be pretty much any of the other ones, Tollens, Phelling, or K2Cr2, but not caminophore because caminophore will oxidize both of them. If you add Tollens, only methanoic acid gets oxidized. The other one does not get oxidized. So we can go with, I think, let's go with Phelling. So if I go with Phelling and I heat it with Phelling, only methanoic acid will get oxidized. The other one will not. And that will result in a brick red precipitate. And then you've got the second one. So what's happening here? The other two are not reacting. Methanoic acid and ethane dioic acid, both of them are not reacting. So this second one is definitely not oxidation because what we were talking about was oxidation. So these two are not reacting. But if you look at the structure over here, that's a ketone. I mean, it's got a Cethyl bond O in the middle. That's a ketone, right? So what do you think? AS, what does a ketone react with? Ketone reacts with the 2,4-DNPH. I mean, ketones have a very specific reaction with 2,4-DNPH. And it gives an orange precipitate when you react it with 2,4-DNPH. Like if you look at your AS reactions, you'll notice that that both ketones and aldehydes, they have this specific identification reaction with 2,4-DNPH, 2,4-dinitrophenyl hydrazine, and that gives an orange precipitate. So we had to come up with a reaction in which only the middle one reacted. The other two did not. The middle one was ketone. So that's how we're going to differentiate. The ketone will react and the other two will not react because they're not ketones. Is that clear?
Yes, sir.
Yes, sir.
So we completed the table and that's again carbon 13 NMR. Just a second. NMR. Now this one. No, that's NMR. KSP. Explain what is das buffer. Hold on a second. So we run no other organic question. Let's do another paper. Let's do winter 20. So winter 24-1. So organic, just a second. So transition metals, still transition metals. Same thing. Who's acidic, who's not acidic? So I'll just there are actually a few reactions like this one. I think this one. So they're saying that phenols can be made. So this is where the questions are. It's a weak acid. Phenols are weak acids. Remember that. Give the reagents and conditions for this reaction. Phenols can be made from phenylamine. So you got phenylamine. That's NH2. And he's saying that phenols can be made from this thing. So how does it turn into OH? That's the question. How do you do that? How do you convert an NH2 to an OH? I just look at the spider chart. It has something to do with the azo-dyes. So if you look at the spider chart for A2, it's this one. So remember, you're at this point, right? He wants this to be converted into a phenol. So what will happen is that you can convert it into NNO2 plus HCl, react it, and it will form a disonium ion. This disonium ion can be used to make azo-dyes. That's it. That's an azo-dye. Okay, we did this in N triple bond N+1. Gets very strongly attracted to the benzene from an activated benzene. And this thing bonds with this. So you get a double bond in between. But this ion is highly unstable. If you warm it with water, it will turn into a phenol. So this is the path. Phenylamine turning all the way into a phenol. So all you have to do is you turn it into a disonium ion and then you're going to warm it. And the whole ion will decompose in water and it will turn into a phenol. So that's what you're going to do. So first thing will be NNO2 plus HCl. You're going to keep the temperature less than 10 degrees centigrade and you're going to tell them that it forms a disonium ion. So it first ends up forming a disonium ion. And then what you're going to do is you're going to heat it or warm it in water. And the whole thing or the whole ion decomposes and it eventually forms the phenol. Is that clear?
Yes, sir.
And this is this part. Like if you open the detailed notes, I think in part number 3, this one. I mean, right after redox reactions, you did nitrogen compounds, and in nitrogen compounds, we talked about the formation of azo-dyes, that dye stuff. To get that part. That an amine, phenylamine, could be turned into a disonium ion. This disonium ion will get attracted to an activated benzene. And it will attract the electrons, it will bond with it, it will form N double bond N, which is the azo group. That's a very stable dye. So most paints are these dyes. But if you turn it into a disonium ion, if you heat it with water, it's a very unstable compound. It will quickly decompose to form the phenol. So that's what's going to happen. So let me just quickly check. This is W20 QP41. Just 1 second. I mean, is he giving 2 steps or is he giving question 7, right? Yep, it's the same one. The other one is, first one is NNO2 plus HCl, and then the temperature, you heat it up. Greater than 10, you warm it with water. That's about it. Same thing. And oh, sorry, heat it. you have to specifically mention that you have to increase the temperature greater than 10. Now, the next one is phenol reacts with nitric acid under room conditions to give a mixture of two isomeric products. So phenol, we're talking about phenol here. Is it 2,4,6 directing or is it 3,5 directing phenol?
2,4,6.
So it's 2,4,6. The lone pairs are going to overlap and the electron density will be higher at these positions and these positions. So the NO2 will get attached to either this position or it will get attached to the bottom position, which is the 4 position. So it's going to be 4-nitrophenol or it's going to be 2-nitrophenol. I mean, this one is 2-nitrophenol. And this other one is your, I mean, this is 1, 2, 3, and that's your 4-nitrophenol. And this happens when you add nitric acid to it. If you add dilute nitric acid, remember phenol is a very highly activated benzene. The electron density is really high. You don't need a catalyst in this reaction. All you need to do is you just add nitric acid. If you add concentrated nitric acid, NO2 will get attached to all 3 positions. As a phenol reacts with bromine, draw the name. So we're basically dealing with these reactions about phenols. Remember, the benzene electron cloud is highly activated because the lone pairs on OH have overlapped with benzene electron clouds. So electron density is really high. So the reaction is like going to be really fast. You don't even need a catalyst. If you do bromination, bromines will get attached to all 3 positions, 2, 4, and 6. If you do nitration, you don't even need a catalyst. You don't need H2SO4 as a catalyst. You need concentrated nitric acid. NO2 gets attached to on all 3 positions. If you just add dilute nitric acid, NO2 gets attached to either one of the positions. So we're talking about this one. That's your white precipitate that is going to be formed. So you had a phenol, and the bromine will get attached to all 3 positions. And that's 2, 4. I mean, the positions are, this is 1, this is 2, this is 4, this is 6. So 2, 4, 6 tribromo phenol. You got 3 bromines and it's a phenol. So they're all attached to the phenol. Is that clear?
Yes, sir.
Now the next one, describe 2 observations that can be made when phenol reacts with this 2,4,6 tribromophenol. That's a white precipitate. Remember that. And since it's reacting with bromine, the other observation would be that the red-brown bromine will get decolorized. So there are 2 observations: red, orange, Br2 decolorizes. And the other one is that you get a white precipitate of 2,4,6 tribromophenol. So you don't even have to write Br2 over here. So write an equation for neutralization reaction in which phenol behaves as an acid. Now the thing with phenols is that they were kind of acidic. So you're supposed to write a reaction. So why were they were slightly better acids? I mean, if you look at the whole acid thing, where's the whole acid thing? Over here, I think. Where we talked about carboxylic acids, we also talked about phenols in the same. As just before carboxylic acid, there was a comparison of, I mean, there was a table made, this one. So remember, phenols are kind of acidic. They're not really strong acids, unlike carboxylic acids. They're very weak acids, but they do react with bases, strong bases like NaOH. They don't react with weak bases like carbonates and ammonia. They don't react with it, but they do react with sodium, and they also react with sodium hydroxide. So if you talk about phenols, there'll be 2 reactions. One of them could be with Na, the other one would be with NaOH. He's talking specifically with a base. So the H will leave, it will ionize, and it will form water. It will combine with the OH ions and form water, and Na+1 is going to take its place. And we also explained why phenols were stronger. Why were they stronger acids? Because when the H leaves, the negative charge over here, it mixes with the electron cloud in benzene. So the negative charge is kind of smaller or weaker. So there's less attraction between the two. The bond is weaker, so there's more chances of ionization happening. So that's the explanation for why phenols are like stronger, relatively stronger acids. So going back over here, I'm just going to write a reaction with a base NaOH. Phenol will lose its H plus 1. So it will lose its H plus 1. The H plus 1 will go and react with the OH ions, form water. And the Na plus 1 that from NaOH will join with the phenol, and that will form the salt. The next one is about, so is this clear, this one?
Yes, sir.
I said you can see that like we're doing the second paper. This is like the third or fourth time that they're actually talking about the strength of acids and bases. So that's kind of important. Again, he's talking about phenols, water, and ethanol, right? So you just open the notes. Phenols, water, and ethanol, right? So phenol, I mean this one would phenol, water, and ethanol. Ethanol being the weakest, right? Phenol, relatively speaking, is the strongest out of the three. What's the reason for that? He's asking for the reason. So the reason is, what about alcohols? Why are they such? Alcohols, you got a carbon chain. It's got an electron donating effect. The negative charge becomes bigger. So there's going to be more attraction between the H plus 1 and the O minus 1. The OH bond will be stronger, so there's going to be less ionization. The OH will be, it would be very hard to actually break the OH bond. So ethanol or alcohols, they are really bad acids. They don't even ionize. They ionize even less than water. And the same thing for phenols. For phenols, you're going to describe that, well, the H leaves. But the negative charge over here is a lot weaker because it overlaps with the benzene electron cloud. So the negative charge becomes lesser. Its charge density is lesser. So there's going to be less attraction for H plus 1 ions. And more ionization will happen in this case. So you just have to describe, and we can just look at the marking scheme as well. So you just have to describe water will be in the middle. The most acidic would be your phenol. And the least acidic will be your ethanol. Is that clear?
Yes, sir.
Yes, sir.
And you can check out the wording as well for the last part. So for phenol, the lone pair mixes with the benzene electron cloud, and for ethanol, you got an electron donating alkyl chain. And you're going to talk about, I mean, the weakening of the OH bond. So we did comment on that, and the other one is that it's just 3 marks. So we pretty much got 3 marks there. The fourth point is about the ease of proton or the attraction of H plus 1 ions, or how there's no point about the four. There's, so the same two correct statement equals 1 mark. I don't know what that means, but it's pretty much the same answer. Anyways, the next one you got the same. So remember, organic, it's kind of pretty repetitive. So benzene reacts with bromine in the presence of a suitable catalyst forming bromo. Give the name of the formula of the other product of this reaction. That's HBr. When you have benzene reacting with bromine, the other product is going to be HBr. This is, where's the reaction? This one. Remember the mechanism that it's whenever bromine reacts, when the H leaves, it combines with the other Br minus one that had left earlier, and they end up forming HBr. That's the other product. So you always get HBr. He's talking about the mechanism, so draw the mechanism. It's Br plus 1 is going to attract the electrons. The Br is going to join up, and it will become a carbocation. And next step, the H gives its electrons back. That's it. Name the mechanism. That's electrophilic substitution. So that's electrophilic substitution, and the next part is step one: reagent and catalyst. What do you need? How do you've got a benzene? How do you put an alkyl chain next to a benzene? That is also electrophilic substitution. That's the same electrophilic substitution that's right at the end over here. That if you want to put a carbon chain and attach it to a benzene, what you'll do is you'll have a halogenoalkane. The Cl will make the carbon polar. It's going to have a positive charge. The positive carbon will get attracted to the benzene and it will join up. The Cl will leave and form HCl. So you're going to do the same thing over here. If you want to attach a carbon chain, the carbon chain originally should be a halogenoalkane. So if I go back to the question, if I want to attach this thing, how do I attach this thing? I'm going to have CH2 and CH3, and I'll have at least have a Cl over here. So the carbon becomes positively charged. When it becomes positively charged, it gets attracted to the benzene, and that's the point where the carbon will get attached to benzene, and that's how the alkyl chain gets attached to it. So the reagents and conditions that are required, the reagent is going to be this thing. It's going to be chloroethane. Is that clear?
Yes.
Yeah. Sina, is this clear?
Yes, sir.
So that is chloroethane, and as always, the other part, the catalyst is going to be AlCl3. Yeah, that's going, or FeCl3 could be a catalyst as well. So we're just going to go with the AlCl3 catalyst and draw the structure of A. What is A? What happens when you, now that's about redox reaction. What happens when you oxidize an arene? So again, oxidation part, that's the alkylation part. Before diastub, you talk about oxidation, right? So oxidation of arenes. Whenever you've got a carbon chain, it just turns into a carboxylic acid. That's about it. Nothing much happens. Just turns into a carboxylic acid. No matter how many carbon chains you got, all of them, they turn into carboxylic acid. So we're just going to turn it into, what we're going to do is we're going to just turn it into a carboxylic acid. But there's one more thing, and that is that the condition is alkaline. So under alkaline conditions, you're not going to get an acid. What you'll get is, because under alkaline condition, the carboxylic acid will lose its H+1. I mean, the OH-1 will attract H+1, and there's going to be an acid-base reaction. So instead, you're not going to get a carboxylic acid. You're going to get this thing. Is that clear?
Yes, sir.
You got alkaline conditions, right? I mean, you should have gotten a carboxylic acid, right? But this H+1 acina is going to get attracted to the OH ion. There's going to be a neutralization reaction. See, is this point clear?
Yes, sir.
And remember this point, that whenever the conditions are alkaline, right, and you got an acid, the acid will always be in this form because it's going to lose the H+1. You can make sure you keep this in mind. You're going to get a salt of the carboxylic acid, not the carboxylic acid itself. So anyways, you got a carbon, and I suspect that they're actually ignoring the OH ions. Let me just check the market scheme for this. Which question is this? Question number 8. So FeCl3, LCl3. Yep, they're actually allowing both of them. I mean, they're kind of ignoring the OH ion. I mean, this is C6H5COO -1. Is that clear?
Yes, sir.
I don't know why they put Na over there, because they never told us that. I mean, the question, they never told us that this is NaOH, right? I mean, could have been KOH. So, anyways, they're accepting both of them. Okay, so they didn't really cut or deduct marks for this. How do you turn a carboxylic acid back to an alcohol? What do you need to
Reduction.
reduction, right? So I mean, it's going to be the reverse of what you the carboxylic acid turning back to an aldehyde, turning back into a primary alcohol. So where's the reduction part? This one. Actually, sorry, this one. Carboxylic acid turning back into an aldehyde is given over here. That's LiLH4. And remember, that's only LiLH4. Aldehydes turning into primary alcohols, for that you can use two reducing agents. One is LiLH4, the other one is NABH4. Same with ketones, you can use both of them, but for carboxylic acid, you need a stronger reducing agent. LiLH4 is a stronger reducing agent. So that's going to be LiAlH4 only. Carboxylic acid turns back into a primary alcohol. And then you've got the benzene ring vanishing. That, remember, is hydrogenation. That's if you add hydrogen and nickel catalyst, all the double bonds in the benzene, there's going to be an addition reaction. And all the alternating double bonds in the benzene ring, they'll absorb all the hydrogen atoms. And the temperature for this is going to be 200 degree centigrade. Is that clear?
Yes, sir.
So we did draw the structure of A. What other things do we have? Identify suitable reagents. We did all of that. That's NMR. Here's another question. You're seeing type of polymerization. So this is about polymerization. So when you've got a monomer that's got carboxylic acid and alcohol, what do they form? They form ester links, right? So this one is about polymerization. This is about the third part, right? At the end of the third part. This is mostly like O levels polymerization. So when you have a molecule that's got carboxylic acid on both sides and alcohols on both sides, these are your two monomers. They will end up forming water in the middle, and they'll end up forming ester links, and you'll get a polyester. So this first one, that's carboxylic acid on both sides, alcohol on both sides. So type of polymerization will be condensation. Is that clear? And
Yes, sir.
and this one as well. This one will also be a condensation polymerization because going back over here, this is also going to be condensation polymerization because I told you that acyl chlorides, they form very good esters. So again, if you just refer to the notes, I told you that acyl chlorides can also do that. They can form really good condensation polymers as well because the carbon is like really strongly positive. So this one will also be a condensation polymer. The carbon is going to be strongly positive. The oxygen will have a lone pair. So these two will get attracted to each other. The H and the Cl will get eliminated. The last one is addition. That's alkenes undergo addition polymerization. When you got a double bond, you got a double bond over here as well. They didn't show it, but if you draw the structure, there's going to be a double bond over here. So when two things have double bonds, that's your addition polymerization must be given somewhere right at the bottom. So when two things have a double bond, that is going to be addition polymerization. And he's saying draw one section of the polymer chain formed including 3 monomer residues clearly. So 2 amino propanoic acid can polymerize, no other monomer is involved. So an amino acid is this thing. It's got carboxylic acid group on one side. This is the last question I'm going to do. It's got NH2 on the other side. And so we're talking about this carbon. It's got a carbon chain CH3 on one side and it's got an H on one side. Right? This carbon over here has NH2, COH, H, and CH3 on it. So he's saying 3 amino acids. So I'm going to draw another one. And I've got NH2 and I've got CH3, I've got H, and I've got another one. So all I have to do now is the H and OH are lost, the H and OH are lost. That's a condensation reaction. You get rid of the H and OH. The H and OH, they form water, right? And you connect them together, that's it. So that's your, so you're saying draw the section of the polymer. So I guess the polymer is still continuing, so the H is lost at the end, the OH is lost at the end. So we're going to draw continuation bonds. Do you make sure you draw continuation bonds? Because we're just drawing a section of the polymer chain, which includes 3 monomer residues. That's it. So this thing is still carrying on. Is that clear?
Yes, sir.
Okay, let's continue. Let's try and do more questions tomorrow, right? We'll probably start with the NMR. We'll do NMR tomorrow. We'll do past paper questions. We've already done a lot of them. Make sure you just revise them. The notes are like complete. They've got pretty much all answers for all questions. Just make sure you try and remember them. We'll do this later. We'll do NMR questions tomorrow. Okay, is that clear?
Yes, sir. Okay, thank you, sir.
Okay, great.
Please send the spider charts as well.
What's the cheese?
The spider charts.
You can send it.
Thank you.
Okay, take care.
Okay, thank you, sir. Good night, sir.